Okay, we're going to take a look at yet another force problem from our new homework system. This is one that I chose because it's a very real-world application. What we've got is we've got a sailboat that is out on the water. I'm terrible at drawing sailboats. So that's a sailboat as seen from above. And we find out, at least for the numbers that I have in front of me, that the mass of the sailboat is 35,100 kilograms. It's pretty heavy, it turns out. Boats are kind of big, usually. Now, my problem says that it experiences an eastward force, and it gives a number. So the first thing I'm going to do is I'm going to set up a coordinate system. So I'm going to say that positive x is this way, and positive y is this way. That's what we normally do. And I'm going to call the positive x direction east. That makes the positive y direction north. Now, it's like we're looking top down on a map, and usually maps have north, up, and east to the right. West is this way, and south is down. All right. Now what I'm going to do is I'm going to start recording some of my information. They say that apparently the tide, in other words, the water is moving, and the water is applying a force. I'm going to call this the force from the water, or force of the tide. You can mark it whatever you want, but it's just a force of the water pushing on the boat. It's a form of a normal force, a physical contact force between two objects. I'm just going to mark it a force. We'll call it the force of the water. And it is pushing, it says, let's see, an eastward force. So it is pointed due east, which is good because that's the way that I've drawn it. The force is 12,900 newtons. Now they also say that the wind is blowing, and that applies a force. I probably should have called that something other than W, because I'd like that for wind now, but that's okay. Let's see, we're going to have the wind pushing on the sails with a force of 89,400 newtons, directed towards the northwest, 45 degrees westward of north, or 45 degrees northward of west. So if we've got straight north like this, they say that it's 45 degrees over. We've got a force like this. I'm going to call it the force from the air, Fa. All right? Now this is at 45 degrees north of west is what they were saying, or 45 degrees west of north. Both of them point the same way. It's up and to the left like this. And the value of that force is 89,400 newtons. We have two forces acting on the boat. The water pushing it this way, and the wind, the air, pushing it up and to the left. And what they ask for part one is, what is the magnitude of the resultant acceleration of the sailboat? Now that's a very dense thing to ask for. Remember, magnitude, when it comes to vectors, they have two things. They have a magnitude, which is the number, and a direction, the way that they point. So when they say magnitude, it just means we're going to solve for the total number. They're not immediately going to ask for the direction. Now, unfortunately, if I'm not mistaken, in one of the later parts, they actually ask which direction it goes in, but we'll take a look at that. All right, first things first, the magnitude of the resultant acceleration. So we're looking for basically the total acceleration for the boat. We're just looking for the number, and then in part two, we'll find the direction. All right, in order to find the acceleration of an object, I have to look at all the forces acting on it. In fact, we want to apply Newton's laws of motion. Now, I've got a drawing here, but I'd like to see it a bit more clearly, so I am going to draw a free body diagram. Here's my boat, and I'm going to put the forces that are acting on it. I'm going to call this one Fw, force of the water, 12,900 newtons. Now I've got one that points up and to the left. This is one that we haven't quite looked at just yet in class, depending on when you are watching this. But it is a two-dimensional vector. I'm going to use purple because it's a combination of my usual red and blue. And I'm going to call it Fa for the force of the air, and it is 89,400 newtons at 45 degrees above north of west. So it's pointed this way. We have an x component, Fax, and we have a y component, Fay. So here's the thing. I'm going to want to apply Newton's second law of motion. Now that I've got my free body diagram, I would do sum of forces equals my mass times my acceleration. Well, my forces are vectors, and to add them up, I need to break them into components and add the components to find my result. So, we're going to need the components of this force. If you haven't taken a look at it already, you can check one of the previous videos where we break a force into components with the dog lifting up on the pillow. So let's find our components here. I'm going to do, for my x component, I'm going to use so, ka, toa. Also check out my vector videos for a reminder of how to work with vectors. But I'm going to use ka, this is the adjacent side, so I'm going to do cosine of 45 degrees times my total hypotenuse, 89,400. Double check how to do that, but it is based off of cosine of 45 degrees, ka equals adjacent over hypotenuse. And then solving for my force in the x direction, at least from the air, the wind blowing on the boat. We end up with 63,215, which is probably to three significant figures at 63,200. You're welcome to keep the 215 if you would like. As I said with the online homework, if you keep to three significant figures, you should be fine. It will accept anything within 1%. Feel free to leave the 63,215, or more accurately, whatever numbers you have, because you're likely to have different numbers. All right, that's one of my components. Now, this is 45 degrees, so I already know that this is an isosceles triangle. I know that my force, my y component, is also 63,200, or 215, if you'd like more significant figures. Now, if you have something other than 45 degrees, we would use sine of 45 degrees equals my y component over the hypotenuse. I'm going to save some time in this video. You can check out some of the others to see exactly how to go about getting those. But now that I've got my components, I can start going through. This one is 63,200 newtons in the x, and this one is 63,200 newtons in the y. I'm going to apply Newton's second law of motion. To do that, I need to split things into the x and y, so I'm going to do sum of forces in the x equals my mass times my acceleration in the x. I'm going to look back at my free body diagram. I have two forces acting in the x. I've got this force, Fw, positive Fw because it is to the right. And what I've got otherwise in the x is this one pointed to the left, so I'm going to call it negative Fax. It's the x component of the wind, the air, blowing on the sails. I'm going to set that, those are all of my forces in the x, I'm going to set that equal to my mass times my acceleration in the x. I'm going to fill this in. We had 12,900 newtons minus 63,200, I believe. Yep. 63,200 newtons equals my mass, which we said was 35,100 kilograms, times my acceleration in the x. I'm going to go through and do some of the math here. I'm going to take this minus that guy. 12,900 minus 63,200. I'm going to end up with a negative number. You might think that's a little weird, but remember, we're solving for vectors. So the negative number just means its direction. Negative 50,300 newtons equals 35,100 kilograms times my acceleration in the x. I'm going to divide both sides to get a sub x by itself, 35,100 kilograms. And I end up with my acceleration in the x being equal to, if I've done this correctly, negative 1.43 meters per second squared. I get 1.433, but again, three significant figures should be fine. All right, now this is not my answer. because this is only part of the acceleration. This is the acceleration in the x. They want the total acceleration. So, this is part of it. We found our x component. We now need to look in the y direction. On the upside, the sum of forces in the y equals mass times acceleration in the y. This one's going to be much easier. I only have one force in the y, 63,200 newtons, and it's positive because it's up. 63,200 newtons equals my mass, 35,100 kilograms, times my acceleration in the y. I'm going to divide by 35,100 kilograms. Do the same thing to both sides. And I get my acceleration in the y being equal to 1.80 meters per second squared. Now this is also not my complete answer because it's my y component. This is the last step of adding vectors. We've found the resultant components. In fact, because of Newton's second law, we've now found the components of our acceleration by dividing by the mass. Now what I want to do is I want to find the total acceleration. Now my acceleration in the x was negative 1.43. Negative means it's to the left. I'm going to draw it to the left and make it 1.43 meters per second squared. The negative tells me the direction. Since I've drawn my arrow to the left, I still have the direction. I also have a y component, which I just found, of my acceleration, which is 1.80 meters per second squared. Oops. I now realize that it's going to point up and to the left, which means I should probably draw this down here so I can see a bit more clearly. That's okay, you could have drawn the y first and the x second. It doesn't matter, you will end up with the same thing. We're going to end up with this. This is my total acceleration. Now the total acceleration we can find, remember this is a right triangle, that's the point of components. We can find this with the Fibrin Theorem. So we can do 1.80 squared plus 1.43 squared. I'm going to take the square root. That is going to give me 2.30 meters per second squared. All right, now that's my magnitude. I now need to find the direction. Now they ask, what's the direction of the boat's acceleration? Let's see, do they have... I think they tell you with a sense of reference which way it's pointed. Let me check real quick. Let's see. Answer in units of degrees and north of west. This is something that we didn't talk about a whole lot, but I've got an angle right here, the way that I've drawn it, where if I go west, if I go this many degrees north of it, this is the angle I'm looking for, theta. So, with this, I can use some of my trigonometric functions. Remember, so, ka, toa. In this case, in case I've made a mistake on calculating that, which I actually haven't, I double checked the numbers, I'm going to use these two components just to be safe. So to do that, I am going to use TOA. And TOA tells me that tangent of theta equals my opposite, 1.80 meters per second squared, over my adjacent, 1.43 meters per second squared. And you will notice that the units cancel out. Tangent of an angle gives us just a number with no units. So this actually works out. I want to find theta though, so I need to get rid of that tangent. I'm going to take the arctan, the inverse tangent, of both sides. That will leave me with theta equals the inverse tangent of 1.80 divided by 1.43. Put that into my calculator. 1.80 divided by 1.43, inverse tangent, and I end up with theta equals 51.5 degrees. And since that's this angle here, I would have west. I'm going up 51.5 degrees. This angle is 51.5 degrees north of west, which I believe is what they asked for. Let's double check. Yep, 51.5. All right, this is how we deal with two forces. Not necessarily nice forces either. One of them points up and to the left, and one of them points straight to the right. You can see that it's the same thing that we've done before. We draw a free body diagram to see our forces clearly. We apply Newton's second law, and Newton's second law, because these are vectors, we have to look in the x direction and the y direction, and sometimes even go so far as to combine our results to find their vector result.